In today's lecture, we will be continuing with the remaining portion of the electrochemistry. Today we are dealing with standard electrode potential. So standard electrode potential is basically uh, the metal rod. For example, there we have learned in the previous class the reactivity series, isn't it? So there the reactivity series actually plays a very crucial role in terms of their reactivity. Now, how do I explain or how do I define this reactivity, or based on what this reactivity matters? The reactivity is based on the ability to actually donate their electron, to lose their electron. So, for example, the reactivity for, let's say, the metals, it's based on like how difficult it is for the metals is it to donate the electron, the valence electron, to form the like the ion which the metals usually form. For example, for copper it's either copper 2 plus or copper 1 plus. For iron it's Fe2 plus or Fe3 plus. For sodium it's Na plus. For potassium it's K plus. For zinc it's Zn2 plus. So that's actually the reactivity which it defines. For example, if there's this metal zinc, how difficult it is for itself to lose the electron, and how easy it is, or how easy it is for itself to lose the electron. So you can say the level of difficulty or the level of easiness, that's what matters the reactivity. So based on that, some metals are more some metals are higher in the reactivity series, while some are in the lower range of the reactivity series, defining some are more reactive while some are less reactive, while the more reactive ones tend to participate in the reaction or donate electrons pretty fast, while the less reactive ones tend to like lose electron pretty slowly, or it's difficult for them to lose electron, or they require very high temperature. Now that transfer of electron creates an electricity or voltage across the terminals, you can say. So in terms of electron, if the electrons flow, electron is what? A charge. It's a negative charge. Now when electron flows from, let's say, one place to another, there is obviously a potential difference generated across, since the charge is being flown. So due to that, this is actually known as the electrode potential, which is produced across that metal rod due to like the transfer of, you can say, the electron, or due to transfer of charged particles. So there is presence of both E minus or electron, as well as the presence of the metal ion, positive metal ion. Now, in terms of this example which I have just drawn here, zinc metal in its ionic state, it has a valence of Zn2 plus. Zinc rod tends to donate electron. This is the zinc rod, or you can say the electrode, which tends to donate electrons, forming positive charged ions. Now, according to this equation, the zinc in its solid state or in neutral state, it is losing electron, donating electron, and forming Zn2 plus ions. Hence, zinc ions from the solution gain electrons to make zinc. The reverse process also happens. How? Zn2 plus gains electron and shifts towards the other direction to form zinc. That means we can say there is actually a reversible reaction being carried out. So which is, it goes on the right hand side as well as on the left hand side. So it's a two-way reaction. So zinc ions from the solution gains electrons to make the zinc solid as well. Now in this state, when an equilibrium is established, the rate of oxidation is equivalent to the rate of reduction. Now over here, you can see what? Loss of electron, and loss of electron is what? Reduction? No, it's oxidation. Oxidation. Loss of electron is oxidation. And gain of electron is known as reduction. Now there is a short form we can remember. Uh, Usually the barrels or like the containers which it holds oil is known as what? Oil rig, isn't it? Oil rig. Now oil rig, this is the short form of oxidation reduction. How? Oil rig means O for oxidation is loss of electron. So these are the short form. And rig means reduction is gain of electron. So this is the term which I usually use to remember which one is like oxidation and which one is reduction. So you can also use this in order to like recall. Now, as I just mentioned, the rate of oxidation and reduction is equal. That means a constant is established, like the forward reaction is equals to the rate of backward reaction, because forward reaction is the oxidation reaction, backward reaction is the reduction reaction. So in that way, the both like the both oxidation and reduction are equal in their rate, in their value. Hence, this this redox equilibrium is established. Redox equilibrium is being established. Now, an electric potential, as I mentioned, is established between the metal and the metal ions. So this is the metal ion. These are the metal ions which like clings or holds onto the outer layers of the metal rod, and this is the metal rod. So in between them, electron tends to flow. So due to the flow of electron, there is a like potential difference, or you can say in other sense that over here this rod is neutral, but over here we have a positive charge. So there is obviously a difference in charge. There is a positive charge, there is no charge. That means there is obviously a difference in charge, a positive charge difference. So due to the charge difference, a potential is created. It is being created across or in between this positive charge metal ion and the metal rod. We cannot measure this potential directly. Like if you say we will be like in physics term, we will be like pivoting or probing using like multimeter, that won't be possible because we cannot probe this tiny, like very tiny metal ion. Like, they're like out of our reach, and the difference is also very negligible. That like it's unrealistic to measure them in such a way. So it's not possible for us to like measure them. So how do we then measure them? The one of the possible way for us, which we will be using in our in chemistry, is by the help of standard hydrogen electrode. Now, what is that? This is an electrode. Okay, this is a zinc electrode. In the same way, there will be the like another electrode where, as the name suggests, it's a hydrogen electrode. So we draw it first. So this is the hydrogen electrode. Now, how it works? Let me explain the diagram in detail. This is the platinum wire, and this is the platinum electrode. This is the gas belcher. Now, this is actually any solution, any sort of solution which contains hydrogen ion. That means this is an acidic solution. Any solution which contains H plus ion is more than enough. And what do we have? Yeah. So now is the part of hydrogen. Now, how do we like since the name suggests it's a hydrogen electrode, that means there should be hydrogen present. But how do we get hydrogen? Hydrogen is like not a metal; it's a gas. How do we do that? How do we deal with that? So we need to produce or provide hydrogen through this topmost part, upper part. Hydrogen gas is inserted, so hydrogen gas in. And from here, after like some like after electrolysis, after participating in the electrolysis or after participating in discharge and other sort of things, the hydrogen gas comes out from this bottom of the well here. This is hydrogen gas out. These are the bubbles forming due to the gas under the water or under the solution. Now here H plus should be, like as I mentioned, 1 mole per gm cube. The volume as well should be 25 degrees centigrade. And since this there is the presence of hydrogen gas, the pressure should also be 1 atmospheric pressure, like the standard conditions. And the equation for this reaction will be H plus that was E minus forming H2 gas. Since we need to balance it, let's, for the simplicity, we multiply a half. We multiplied a half in order to make or skip this one more. So this is an like unusual thing we usually do, because in equation what do we do usually? We multiply with a numerical, like integer value, not a fraction. We multiply with the integer value, but in this case, for our convenience, we multiply with a half on all the side. Let's say if we didn't multiply with half, then we need to multiply every side with 2. Then in order to make this 2, like this make the most 1, what do we need to do? Divide all the sides with 2. That's what we just did, but we just wrote the final result, which is half is 2. Now, I mentioned, like we'll be using electric potential of the metal by using the, or by taking help from the this standard electrode of hydrogen or standard hydrogen electrode. Now there might be some question, uh, where like isn't hydrogen also having certain potential? Like since zinc, we are using zinc when, well, like when zinc is being used, there is a like potential. A zinc electrode is used, zinc solution is used, then isn't there like obviously there was a potential? Then isn't hydrogen also going to have a potential? And if something, let's say we need to find x, x is the potential of something. Now if the others, like if we want to find the potential of x, and we like let's say this is the potential for not f, let's for z, we apply z here. Z is the potential value for zinc, and hydrogen has the potential value of x. Then you might be thinking, if we add to, like both of them, or if we subtract both of them, we'll be getting a number which also we don't know. Like there isn't like, in order to find the unknown value, we need all the other values known, isn't it? Like all the other values should be known. If two of the variables, if in equation x plus y equals to 10, if both the values are unknown, then how are we supposed to know what is the value of x, isn't it? One of the value we should be, like, it should be known to us. Same goes for here. One of the values should be known to us. That's where comes this part, like hydrogen electrode. Why are we using specifically the standard hydrogen electrode? Because it has a potential value of 0. So its potential value is 0. So like there is no, like, it doesn't have any effect. It just acts as a like base, or acts as a norm, not like it acts as a, for example, in xy axis we place y equals to 2, but how do we know y equals to 2? Because we started start the counting with from like which point y equals to 0, right? If we consider y equals to 0 as a norm, or as the standard, as the starting point, and then we start to calculate, count the number of steps. In the same way, we're just dealing with this part where this is, let's say, the starting point, the starting part of the starting electric potential value. From here we tend to calculate the value for Zn2 plus. So if the equation was, let's say, x minus y equals to 10, now without knowing any of the values, how are we supposed to know? So let's say we need to find x, and y is given as what, 0. So x minus 0.00 is equals to 10. So there, from here we got to know that okay, x is actually equals to 10. So in that way we'll be able to find the electric potential values for the metals or other sort of like electrode potential electrodes, reactive metals. It could be metals or it could be some other gas if they produce uh, if they produce the potential. For example, chlorine. We'll be doing one such example to this lecture. So without further ado, let's do a couple of examples. So at first, let's try to find the difference between zinc, the electric potential value between zinc. Now, using the data booklet, there is a page where there are written the electric potential values of the reactive metals. So there are the ionic equation given there, Zn, for example, Zn minus 2e minus, or we can say Zn taking the minus 2e minus on the other, like on the right side. So the equation will be Zn2 plus 2e minus. So over there on the data booklet, beside this equation, there will be written the electric potential value for this equation, which will be given actually negative 0.76 volt. So using that value, we can do our calculation or do our other stuffs. So let's draw the diagram. Let's say this is actually a voltmeter, and this is zinc, and this is, let's say, hydrogen, standard hydrogen electrode, the Belger. That's our beaker. Remember always this bottom hole of the, like, this bottom part, this bottom hole should always be submerged under the solution. Okay, this should not, or this should never be above the solution level. So this should always be under the solution level. And do always level the diagram, which part is what. So H2 in, H2 gas in, this is H2 gas out. The solution is 1 mole per dm cube of H plus, and 25 degrees centigrade is the temperature. And this is Belger, this is platinum ware, this is electrode, platinum electrode. Then this is Zn electrode. On the solution, we have like 1 mole per dm cube of Zn2, some salt which contains Zn2 plus ion, and which actually 1 mole per dm cube. This is also 25 degrees centigrade. Now, thing is, we have to, uh, yeah, so we have to draw one of the part, like one of the element. We have to add one more specific substance over here, or we can say a material, which is the salt bridge. Now, what does the salt bridge do? The salt bridge, before going to salt bridge, when this reaction actually happens, what happens? One of them loses electron, another gains electron, isn't it? So let's say zinc is losing electron. So the electron is being flown from this side to the other side, or from the other side to this side, any one of them. That means hydrogen is also actively participating in the equation. That means hydrogen also either losing or gaining electron. Is it? As a result, what is going to happen? The solution is either going to, the amount of ions present in the solution is either going to get decreased, or what? Is either going to get increased. Either of them is going to happen, isn't it? So if that's the case, then we always need to remember that we need to place, like, we need to regain that situation. Or for example, is, let's say, the motorcycle, this, like, it runs on what? It runs on petrol, or it runs on the fuel. If the fuel ends up, then how it's going to run, how the process is going to happen, how it's going to work. It's not going to work. Similarly, if all the, like, the iron, How this electrolysis happen? Electrolysis happen due to the presence of the free ions, which helps to flow the like to conduct electricity, isn't it? But if ions are all discharged, that means no more ions are present there. Then who is going to conduct electricity? If no one is going to conduct electricity, that means there won't be any flow of charge, so no electric potential will be created. That's why we need a salt bridge, which should be like salt bridge is this salt bridge is actually made of the filter paper, the filter papers which we use in chromatography and other sort of like biological laboratory experiment as well. The actually the filter paper is actually the one which we usually tend to make the funnel. So in the experiment. So that sort of paper strip this. So that paper strip, this is the paper strip. This is going to be submerged, or let's say this is the solution. There, this paper is going to like we are going to dip it there, soak it with the salt solution, some sort of salt solution, and place it on top of like into the two solutions on the two beaker by inserting them or dipping them partially towards the solution, hence like trying like making a contact in between them. So this is a solid bridge which will by itself decide where to flow which electron. So if let's say we have n potassium hydroxide, okay, potassium hydroxide or potassium sulfate, let's say potassium sulfate A2SO4. Yeah. Now if let's say Zn2 plus gets eliminated from this part, all the Zn2 plus are all discharged. That means that no more Zn2 plus, no more positive charge ions are here. That means what? We need more positive charge ions. In that case, potassium ion is going to move to this solution. If Zn2 plus get discharged, that means from on the like on the other side, the negative charge is going to get discharged, isn't it? If one in one side positive charge is getting discharged, on the other side the negative charge is going to get discharged. That means the sulfate ion is going to move to the other solution or in the other direction, or vice versa will happen if Zn2 plus concentration increases. We need to reduce the Zn2 plus's concentration. How can we do that? We need to provide more negative plus ion. So sulfate will be produced to get provided towards this solution. Hence, potassium will go to the other solution. I hope this is making sense. Like it is something like this. If negative charge increases, that means negative charge becomes more dominating, but we need a neutral situation. So we have to diminish or reduce the effect of this negative charge. So how can we do that? We have to increase the amount of positive charge there. And if positive charge increases, or yeah, positive charge increases, and the other way we are just going to reduce the amount of negative charge. That's it. Now the part of the electron, the, the electron potential value. So in the data booklet, it's given negative 0.76 for the zinc. Now, how are we going to write it here? We need to remember one thing, that the electron always flow in certain direction. Since the electron need to flow in certain direction, for right now, like we are not dealing like for right now, just for the moment, just don't think about like in which direction electron is going to flow. Just for like carry on with me. So since the electron potential value is negative 0.76, we're going to place here negative 0.76. And in this environment, like in this situation, the way these materials are plotted, like zinc electrode is on the left side and hydrogen electrode is on the right side. We're going to consider this as the left side as the positive terminal and the right side as the negative terminal. Just for the time being, just follow up. We'll be after few examples, we'll be actually knowing like how do we define where the positive and negative terminal will be and in which direction the electron is going to flow. So just bear with me. So that was the first example. The second example will be, let's say, okay, before doing that, what type of reaction or what type of diagram was that this actually is a half cell containing metals and metal ions. These are like half cell equation, like half cell diagram. So what does half cells actually mean? Half cells are like one of the cell has only electric potential, the other part does not have any electric potential, which is zero. So here the main thing or the main potential is based on whom? Zinc, isn't it? And hydrogen is just a referral, like referenced electrode potential or electrode value, electrode. So based on whom a zero electrode potential or like starting electrode potential is there, then like, hence this electrode potential value is actually based on whom? Actually based on or it's based on zinc. Zinc is the one which is actually like influencing this electric potential value. That's why it is known as the half cell. There will be a full cell where on the other side will also be a metal. Like once like this is actually used in order to like to analyze or to find out what is the electric potential value. Let's say we don't know the electric potential value of zinc. In that case, we will be using this experiment to find out what is the electric potential value, because the reading we just got negative 0.76. Obviously, we took it from the data booklet, but how did we get it in the first place in the data booklet? We got it in the data booklet by using this system, and we got the reading on the voltmeter. So that's what like we are like mimicking here. Like we're sort of mimicking like what we did in the real life, how this experiment was done. So just that representation of how the experiment was done in the like pen and paper. We're just like drawing the diagram. Another example could be a half cell containing, let's say, copper and copper 2 plus ion. So half cell or Cu 2 plus ion. So that's also will be the same pattern. Copper electrode and copper ions on the left side, let's say, and hydrogen standard electrode for electrode on the other side. And same pattern occurs. Uh, Hydrogen in and hydrogen out. H2 in, H2 out. Just follow the previous diagram. I'm not like writing all of the terms clearly. And this is the salt base for the time being. Just write salt base. You don't need to write what is like what are the like, components in the salt base. Like just don't consider right now. But do write water present in the solution H plus aqueous 1 mole per dm³ with a concentration 25 degrees centigrade, 1 atm or 1 atmospheric pressure. Only pressure is included where gas is being used. Since on the right side of the like the electrode, like hydrogen gas is being used, so we are just going to mention the pressure should be 1 atmospheric pressure. While on the other side, on the left side, see we won't write actually like the pressure. We will just simply write CO2 plus aqueous 1 mole per dm³, and just 25 degrees centigrade, the room like temperature. This is copper electrode, copper electrode, and this is Alex. We were obviously like already wrote the CO2 plus ions present here. So the equation, which is actually the electric equation, this is the equation. So Cu solid, copper solid, and using this equation in the data booklet, this exact same equation is given. Just write that and write the electric potential value on one side of that, and also here the electric potential value, the voltmeter, and is the positive and the negative terminal. Also, we should have been like written on the previous example as well about our the equation we found. So that should be Zn2 plus aqueous plus 3 minus. We tend to write the only reduction reaction. So this is C, the reduction reaction plus gaining of electron. So we do write the reduction. Like this is a like a standard method. So you can write the other way, but this is more like the bookish method. So, yeah. And this is the second example. And I forgot to mention this is platinum ware. This is platinum electrode. You got the thing. You just like write all the things which you need to mention because they ask you to like level and like level the diagram until our like draw and level the diagram. So there is also mark including like containing contained in the diagram. So that's it. And the last example, which like we said in like in the at the beginning, that we might have like the gases being used as electrodes, like similar to hydrogen. Some other gases could have been used who will be having some electric potential value. So that's the same way we will be using actually, like we'll be drawing a half cell of non-metal in different oxidation states. So for our term or our part, we'll be using chlorine. Also remember, for these non-metal gases, I'm sorry, non-metal elements or non-metal gases, we will be using platinum electrode. Why? Because those who are metal, obviously they are able to like form ions easily. But those who are non-metal, those are like they could be simple covalent molecules. They could be simple, like they can have simple molecular structure. Obviously, they are not going to have like metallic ionic, like metallic electrostatic bonds in between them, isn't it? They won't be like electron and like the for metal. What happens? There is the presence of the positive charge metal ions, and there is the C of delocalized electrons. That has the bonding between them, like the electrostatic process of attraction. That means they are free to like conduct electricity. But in case of non-metals, they don't have that conveniency as like the metals to conduct electricity. So platinum electrode will be used for the conduction of electricity. Is used. Now, if we draw the diagram in the same manner as we driven like hydrogen, there will be a second bell jet on the left side. So let's draw it on the left. Let's say we're drawing a very like similar mirror image. This is our first solid phase solution. And just let me draw the part of the chlorine only, and rest you do, like if you can draw by yourself, following the other previous example. So chlorine gas in, and from here we are getting chlorine gas. This is our. We didn't need to include actually our chlorine because we'll be getting what? We'll be getting a solution. Okay, yeah, we can actually say like chlorine is getting out. So Cl2 C out. But in the solution, there is the presence of Cl minus aqueous, 1 mole per dm cube, and 25 degrees centigrade. Since there is the presence of our gas, so 1 atm solid bridge. And finally, the main thing we need to write is chlorine gas gains electron to form 2Cl minus gas, the aqueous. And in data booklet, you will be able to find the electric potential value is given as positive 1.36 volt. We are going to consider the left side as positive terminal, negative terminal on the right side. Hence, the value is 1.36 volt. Okay, so that's our part for half cells. Now we are going to consider the two half cells. Like, let's say we have one of the half cell as copper, the other half cell is zinc. Now we are going to combine the zinc and copper. Let's say we have found already the electric potential value of each of them. We found the electric potential value for copper as well as zinc. Now we are going to combine them two in order to see what actual electric potential value, like what in a cell in a battery actually what happens. So this is actually sort of the reaction actually taking place inside like the large battery, for example the IPS batteries or UPS batteries. So the bigger batteries, which are the car batteries, where we can see the 12-volt batteries. So that sort of battery, this sort of reaction is taking place. Not in the pencil batteries. The pencil battery is like some other sort of similar, but similar concept is being used, but some other like type of thing things are used because they are like having a very mobile and compact shape. So yeah, let's do this part, which is two half cells. Let's take two half cells as Zn 2 plus and Zn and Cu 2 plus slash Cu. So copper 2 plus ion and copper, Zn 2 plus ion and Zn. Drawing the diagram, this is the electrode, there's the voltmeter. Obviously, now we will be requiring voltmeter to find the total electric potential value, like the amount, the total potential actually we are receiving due to the difference between their potential value. Now this solid bridge we will be drawing it in this way because we will be having a very thorough, detailed diagram now. We'll be explaining each of the terms, which one will be positive terminal, which one will be negative, which one to consider, which one not to consider. Electrodes for copper and zinc. This is the solution. There's the solution. Here, this solution contains Zn2 plus aqueous 1 mole per dm cube and 98 Kelvin, or you can say 25 degrees centigrade. So we usually in chemistry's term, we tend to use like the Kelvin, so that's better to use. Then the solution contains U2 plus aqueous and 1 mole per dm cube at 298 Kelvin. Because 298 Kelvin is equivalent to 25 degrees centigrade. 0 degree centigrade is equivalent to 273.15 Kelvin maybe, but for approximation let's say 273. So room temperature is 2 plus 25, like 25 degrees centigrade. For if this is 0, let's say if this is the 0 value, 0 is equal to 273. That means 25 degrees centigrade means what? 0 plus 25 done. So if 0 is 273, then we can substitute the value for 0 as 273 plus 25. This gives 298 Kelvin. Now, what do we get in the solid bridge? Before that, let's write each of the equations to E minus Zn E minus potential equation minus 0.76 volt. Do don't just blindly believe in me by like writing these values. Do go to the data booklet and see by yourself where are the values, because in exam time you need to find it by yourself. V minus and copper and the potential value is given as 0.34 volt. Now, what does the solid bridges contain? Solid bridges, like in this case, let's say the solid bridges are, we have NO3 minus, the nitrate ion and the potassium ion. Plus that means KNO3 actually. Here we have what? KNO3. So NO3 minus will be moving to the left side and potassium will be moving to the right side. I'm giving arrows to represent them. Let me draw with different arrow, colored arrow. So nitrate going on the left side, potassium going towards the right side. Okay, so that's basically it. This is salt bridge, salt bridge. Finally, we have a potential value of total electric potential of 1.10 volt. Now, in this case, we are considering negative terminal to the left side, positive terminal to the right side. You might be seeing what happened just. We used so far positive to the left, negative to the right. What just happened? Just bear with me. Previously, we did half cells. This time, we have two half cells. So that means two half cells mean what? One full cell. Obviously, one side will be having a positive, another will be negative. Now, which one will be positive, negative? Depends on the reactivity. How high the reactive, like how difficult it is to react, like for it to donate electron, and how easy it is for that element to donate electron. That will be the determining term, like the determining concept, which will determine who will be positive and who will be negative terminal. So let's have a thorough detailed explanation. Now, the electric potential value for zinc is what? Negative 0.76. So they do tell you to like write this sort of like experimental concepts. So you'll be need to draw the diagram. You'll be asked to draw the diagram as well as define the diagram. So you'll be saying in this way. So I'm writing the first one. Do follow this sort of method. Only like this is very simple. Just simply you have to replace the values for the metals when different question is asked. So the electric potential of Zn2 plus slash Zn half cell is what? Negative 0.76 volt. Electric potential of Cu2 plus slash Cu is positive 0.34 volt. Now the electric potential of Zn2 plus slash Zn is more negative, isn't it? It's more than Cu2 plus slash Cu. That that's much more visible over here. Oftentimes you will see both are positive. That time also you have to think wisely which one is like the lower value. The lower the value, that's more negative, isn't it? Let's say we have a value 2 and we have a value 4. Which one is more negative? This means which one is more closer to like 0 or which one is more closer to, let's say, to the negative side. So if this is 0 and this is the negative part, so which one is more nearer to negative? Obviously 2. 2 is more nearer to the negative part of the like number line compared to 4. Compare is already like 2 more than this value 2. So that means this is far more behind, like this. The difference is far more greater. So that's what it's actually explaining. That means since the more negative the terminal, the value, the negative the terminal, or the more negative the terminal which is like the having the lower electric potential value, that's our negative terminal. In this case, Zn2 plus slash Zn. Now you will get your answer. So Zn2 plus Zn is the minus V pole or terminal, negative terminal, negative terminal, and Cu2 plus slash Cu is the positive polar terminal. Now if we go back to where we started, if we see here, see the copper's electric potential is 0, like 1.36. Like over here, we will be we will be simply consider while finding like the half cell, while analyzing the electric potential value, we will be considering the metal part. Okay, the metal or the element which we are finding, the electric potential value for which we are finding, we will consider that as the positive terminal. Okay, and the hydrogen electrode potential, like hydrogen electrode, standard hydrogen electrode, we will be considering that as a negative for all sort of like finding the values. Same goes for like metal, same goes for like the gases. So the elements or the electric potential value which like for whom we are like trying to find, in this case let's say chlorine is the element for whose electric potential we are trying to find, that is going to be in the positive terminal, and hydrogen will be on the negative terminal. Now this will determine in which direction electron will flow. But for the like, two half cells forming one complete cell, the one which is having more like greater value, or like the greater value, that will be positive terminal, and which one will be lower value, that will be the negative terminal. That's what is being said here. So the one which is the negative terminal, that shows us oxidation. Zn2 plus as Zn shows, or let's say this half cell shows oxidation, while Cu2 plus slash Cu half cell shows reduction. Now the electrons, that means flow in the direction from left to right. In this case, electrons flow from left to right, like based on the situation here, or we can say from like trying to observing this part from the lower terminal, from the negative terminal to the positive terminal. minus V to plus V terminal, or we can say lower potential to higher potential. You just need to write any one of these three, like either right, left to right, left to right. In this case, if let's say I have drawn copper on the left side, zinc on the right side, then the situation would have been reversed, isn't it? This would have been become positive, this would have been become negative. In that situation, the electron will flow in which direction? Negative to positive. That means from right to left in that situation. But in this case, since negative this and positive is on the right, so left to right. So it's better to write like the terminal, like from this terminal to that terminal. That's why, like you will say, you will write that electrons flow from negative to positive terminal, which in this case is from left to right. So that will actually define both like the general term as well as the term which actually implies for your case. Now we come to the solid bridge. Solid bridge is made of strip of filter paper. Now this filter paper is soaked in either like, soaked in solution of either, like anyone would have like been fine. So they are like KNO3 and NaNO3. Use any one from this four, K2SO4 or Na2SO4. So if in exam, if you have learned KNO3 or NaNO3, and if in exam gave you K2SO4 or Na2SO4, don't get like confused because any one of them offer like is fine. But use them like any four from them, any one from this four. Now this salt bridge allows the movement for ions. Salt bridge allows the movement of ions between the two half cells. Between the two half cells. Though the salt bridge does not allow the flow of electrons, salt bridge does not allow flow of electrons. Because remember, electrons only flow in metals. Electrons does not flow in other components except graphite. Graphite, though it is considered as having a property of metal, but in other components, electron never flows, ions can flow. Now, by using the salt bridge, ionic balance is maintained. So by using salt bridge, the ionic balance is maintained, which I just mentioned. Like if any one side have a shortage of, let's say, ions, or the ions value decrease or increase, then we need to rebalance them. So yeah. Now, how do we calculate E cell? So E cell is like we calculate it in this way: the positive terminal value minus the negative terminal value. So this is positive minus the negative. Now the negative means what? The lower potential value. This could have been another positive value, but we are subtracting the smaller value from the higher value. This gives us a value of positive 1.10 volt. Oftentimes you will see we are getting negative electric potential. That's also correct. No need to like get panicked. That's also correct. So there's this note you need to consider. The point to be noted is more negative the more negative terminal represents oxidation, while more positive or the positive terminal represents reduction. Okay. Now the like generally anode is the oxidation. So these are like general terms. So just remember that generally like anode shows oxidation and cathode shows reduction. Here like Zn is what? Zn is like in terms of electrolysis. We have observed that generally like which one of like how do we know actually which one of them is anode and which one of them is cathode. So now like I'm describing that part, like which part is actually like anode and which part is actually cathode. So the information I've given here, the most positive or negative terminal represents oxidation and the positive terminal more positive terminal represents the reduction. Or simply if we don't consider the negative positive terminal, just say the more negative value represents oxidation. Okay, the more negative, let's say potential represents oxidation, and the more positive potential means the electrode potential value represents reduction. Now how do you know which one is oxidation reduction? Now I'm explaining that generally anode shows oxidation, anode is oxidation, and cathode is reduction. So this will help you to identify which one of them are actually cathode and cathode. This is another point to be noted. This is also very important because they do often ask. Here, in our case, zinc is like oxidized, so it is the anode. In our case, in this case, Zn is oxidized, so it is anode. Despite it being the negative terminal. Now, I don't know about like you, but often like I used to have this confusion that in electrolysis we use the cell electrolysis. We use positive like the cells in order to like have electrolysis. We consider the positive terminal as the what? The anode, and the negative terminal as cathode. But that doesn't work here. That's not the same thing as here. See, here we have a negative terminal, but that's acting as an anode. But consider there in anode what happened? In anode, that gained or that attracted what? The negative charge particles. And negative charge particles came there and did what? It did oxidation, isn't it? If let's say there was Cl minus was attracted towards the anode, the Cl minus what? Lost electron. 2e minus showing what? Cl2. Oxidation is loss of electron. Similarly, here oxidation is happening. That means that's the anode. So here anode is like determined by actually who is being oxidized, not the terminal, the positive negative terminal. Okay. So this is the thing. Be cleared about this term. So I don't know if we are confused or not, but I used to get confused. So that's what it is. So this is actually not that, but based on our values, we should consider that. And one more thing to like consider the E cell. So the E cell is actually like reduction minus the oxidation value. So the like reduction terminal minus oxidation, or we can say positive, like anyone which helps you to like remember. So I used to take notes of like any one of them. Like I used to remember this in this way. So the bigger minus, like which one I need to subtract from which one, which potential value is needed to be subtracted from which one. So bigger or the larger value minus smaller or the lower value. Like this doesn't mean like division. This means like either of them. Like it maybe like it means maybe bigger means sometimes bigger means like we think bigger means very big. That's not the thing. That means like bigger by bigger I mean like it's a larger value. Let's say greater value. So that's what I meant. So for simplicity, let's just write one term. So bigger minus smaller, or larger minus lower, something. Yeah. So there could be other like other examples. So I would highly suggest do the examples. Let's say you have other examples of Zn2 plus Zn and Ag plus slash Ag. This half cell, this is one of them. Let's say the other one is Cu2 plus plus Cu and Fe2 plus Fe. Now remember one thing, in case of in case of we don't have, let's say, metals, we obviously need to use what? The Belcher. So I'm just saying in this case that there are half sulfurs fluorine or half Cl2 slash Cl minus and Ni2 plus slash Ni. So plus, yeah. So these are the three examples which should be done by yourself and you should try actually. Yeah. So this is Ag plus Zn2 plus Cu2 plus. This is Fe3 plus and Fe2 plus or Fe2 plus Fe3 plus. And here we have Cl2 plus chlorine and nickel as our electric potential values. So I'm sorry, not the electric potential value, the half cell. So the chlorine on the left side, which is our uh, the chlorine itself is not a metal, so we will be obviously using the Belger, the glass Belger. So using the platinum electrode, and nickel is the metal, so we can use the simple electrode over there, the nickel electrode. And salt bridge remains same. Salt bridge is the among the four, anyone would be used. The next term is the purification of copper. So purification of copper is done in using the electrolysis process. Purification of copper. So it is based on electrolysis using the cells. This is not done using the electric potential values, rather using a cell battery electricity. And on the positive terminal, there is impure copper, and the negative side is the pure copper. So we have already seen that how copper electrolysis happen. That copper is discharged like reduced, or no, it's oxidized. Copper is oxidized from one terminal and it reduced on the other terminal. So using copper as the electrode, since we are using here copper as both the electrodes, so this is also going to happen. And pure copper is deposited on the other part. So let's see, like using solution, let's say CuSO4 aqueous. And as I mentioned earlier, some of the like copper deposits to the bottom, and here impure copper, obviously there is some impurities, all of them get discharged, like all of them, sorry, either all of them get discharged or all of them like ionizes to the solution. Here are some sludge formed. Now what are sludge? Sludge are like the impurities. So this is anode sludge being formed and like sedimented towards the bottom. Now, impure anode contains this impure anode or impure copper contains our Ni, Zn, and Ag. So nickel, zinc, and silver impurities are there. Now, when copper goes into the copper goes into the solution at the anode, the copper actually like discharges or ionizes. Here also there is the presence of what? Copper as well. So copper, but the impurities are these three. Now copper from them is like undergoing the anode reaction. So copper undergoes what? Copper undergoes this reaction by impurity. These are impurities, and copper goes into solution at the anode. Then what are we left with? The silver remains as the metal. Silver does not go under like any sort of reaction. We will just see why is it, but silver remains as metal, so it does not perform any sort of oxidation or reduction. This is due to the like electric potential values. Then we are left with zinc and nickel, which actually dissolves to make Zn2 plus and Na2 plus ions. So that means they're actually what? Oxidizing. They're actually losing electron besides copper. Now, how do we explain? So we can explain, but at first we need to write, let's say, the anode reaction. Anode reaction, the main anode reaction is copper solid being like undergoing or oxidation reaction, F plus 2E minus, and the cathode reaction is Cu, Cu, and sorry, Cu2 plus. Actually, this is actually Cu, not Cu2 plus over here. 2 plus aqueous and gains electron forming Cu solid. So what actually happens? Based on actually electrode potential value, we have to define what is like undergoing in this reaction, or what is undergoing into them, which defines them, who will be forming the ions, or who will be undergoing oxidation or reduction. Then the electrode potential value of it is negative 0.76 volt, and for silver it is using data booklet. You can obviously see. So I'm just taking the values from the data booklet. The positive 0.80 volt. Then we have copper, gives copper Cu electrode potential equals to positive 0.34 volt. And finally we have Ni2 plus 2E minus Ni or nickel, so having a potential value of minus 0.25. Oftentimes you will see I'm not writing the notes, or I'm not writing the answer. So the dictation which I'm giving, try to write that. If like you are unable to like write it by yourself, the dictation, go on to the like rewind the video and like try to capture which are the keywords I tend to mention and write those as your answer. So it's the thing which I'm going to do now. So here are like the four electrode potential values given. Now which one of them is like the lowest? The lowest is what? The negative 0.76, isn't it? This is the lowest value, and the highest is 0.80. Now the one which is highest, that will show what? That will show, we like already saw that that will be showing us reduction, isn't it? That is going to gain electron. But since silver has not participated in oxidation, like Ag plus ion is not never formed, isn't it? In this solution, we have like silver as the impurity. Ag plus has never been formed. If Ag plus is never formed, how it is going to, like how Ag plus is going to gain electron? Since we don't have Ag plus, Ag is going to remain as metal. That's what is being said here. Silver is remaining as metal. It is not performing any equation. That's why it deposits to the bottom. Actually, this anode sludge is mainly silver. So silver is sedimenting to the bottom without participating in any reaction. That means let's say silver is eliminated here. After elimination of silver, we have zinc, copper, and nickel. Among these four, which one is having the greatest amount of oxidation value? Like, yeah, which is having the like highest electrode potential value? Copper. And which one is having the lowest? The lowest one is having like, which is having the electrode potential value, which is the zinc. Now, like copper, since it has a greater electrode potential value than nickel, and nickel has greater electrode potential value than zinc, isn't it? The negative value for nickel is much more like it is, because zinc is much more negative than nickel, isn't it? That means copper will tend to prefer to reduct, like for reduction, while zinc will be preferring towards oxidation. So zinc metal will oxidize, hence losing electron. That means Zn2 plus ion will be formed in the solution. After forming Zn2 plus ion in the solution, what are we left with? We're left with nickel and copper. So already we have what? Copper 2 plus ion in the solution, isn't it? We don't need to form copper. We don't need to form copper because copper 2 plus ion is already in the solution. We are using solution for CO2 plus. So that means already CO2 plus is in the solution. That means this copper is actually going to get discharged to the cathode, forming out pure copper. That means CO2 plus from this solution already being existing, that is going to get like reduced and forming copper. But in the silver case, we didn't have any Ag plus. Ag plus was not there. That's why we couldn't like reduce it. But since copper 2 plus is already in the solution, we don't need to even discharge, like we don't need to even ionize it from this impure copper. We can use it and it will discharge to the pure copper. So that's basically it. Now, if calculations are being like asked to be shown, we can do it in this way that let's say the current is being applied or the current being given to you is 20 ampere. The time is let's say 36000 seconds or 10 hours, which is actually, and they are saying that 225 gram of copper is deposited on cathode. So they're asking you to find or calculate percentage of current wasted dissolving impurities. Dissolving impurities. Okay, so calculating the amount of the percentage of current like wasted dissolving impurities at the anode. At the anode, because at the anode they are being dissolved. Now this is the copper equation which is actually taking place in the cathode. We have only information for that because how do we know? They are giving us copper as deposited to the cathode, so that means we are going to use that information, the cathode's information. So the change in mass is given as 225 gram. Okay. Now Q equals to IT. By using that, we can get the total amount of charge is 72,000 or yeah 720,000 coulomb. So this is the total amount of like charge being produced here, isn't it? Now if 225 gram is being formed from 720,000, this amount of charge, that means 63.5 gram of copper will be deposited due to how much? At first, let's say 1 gram of is being deposited due to how much? So 72,000 divided by what? 225. That means 63.5 gram will cause how many or how much of charge? That is going to be 720,000 divided by 225 into 63.5, isn't it? So this should give us a value which will be, just give me a second. Okay, before doing this, we can do one more thing, which is let's say for the time being. So as I mentioned, like as I'm saying, let's say using the equation Cu2 plus 2e minus gives us what? Cu solid. So Cu solid is given. So 63.5 gram, we can say from here, it is being produced from 2 mole of electron, isn't it? So 2 farad. So 2 times 965,000 is forming what? 63.5 gram. So the other way we can write 63.5 gram being formed from 2 into 965,000 C. That means 1 gram is forming how much? 2 into 965,000 divided by 63.5. Therefore, 225 gram is forming how much? 2 divided by 2 into 965,000 divided by 63.5 into 225. You might be saying why I used the previous part, like which one I was using, like which the method I was using previously. That method is another method, but it will become lengthy because that takes a lot of conceptual thinking. So this is a better approach. So this will be like much more easier. So since like unitary method is being used, so this gives us a value of 683858.27 C. Now, like already we found Q equals to IT, which they gave us. So that was how much? 72,000 Coulomb, and this is the Coulomb we found from this equation. Now, if we find the difference between this Q is what? 720,000 minus 683888.27, and if we find now the percentage of this Q, we can simply get what? The difference was actually 36141.7. So 36141.7 divided by what is our like actual value, the current which they have given us 683,888.27 into 100. This will give us a value of 5.3%. Okay, so that's how we do it. So you can rewind it and you watch it. One more part is left, which is our Nernst equation. That one will be a very short concept, so that one will be covered in the next lecture. Thank you, take care.